Thank you for the invitation. And yes, in the spirit of the workshop, what I want to talk today is about two recent works from my group, and in collaboration with these great people, including my colleague Ankur Moitra. And essentially, like, one of them will have a very clear connection to distribution shift. The second one might be a bit less, but then I will explain towards the end what is the hope of connecting it to distribution shift. So let me get started. So yes, so the first work we'll talk about the task that I think all of us are wondering about is how to detect and intervene on distribution shift brittleness of our models. And kind of, as we all know, it is not only that, in the face of distribution shift that our models make mistakes. The point is that they also make consistent mistakes, because again, all models make errors, but the trouble starts when, and that's where we talk about the distribution shift, when these mistakes are consistent. So we can imagine that, I have a bunch of cats that get classified correctly, but then there is also a bunch of cats that are classified incorrectly. And then you realize, if you think about it and look at them for a longer time, maybe it's about, cats being inside versus cats being outside on the grass. Okay, so you realize that maybe model was trained more on the indoor cats, but then, kind of was failing to generalize well to outside cats. And of course, we can have this kind of insights and we can, derive some lessons from them. But the question is, can we identify such systematic failure modes in a systematic way? Okay, and that's kind of the goal we are after. So in particular, the way we want to operationalize that goal is by finding what we will call a direction of hardness. So in some sense, we would like to find a way to embed kind of, embed images in a line according to hardness. And whenever we have a new input, we kind of can classify where on the scale of hardness it lies on. Okay, and so that's the goal. The question is, like, how do we go about accomplishing this? And kind of the key idea here is to try to frame the question of failure of model prediction as a prediction task itself. So instead of trying to predict, instead of trying to predict for a given input what is the correct label, we just want to solve a meta task of trying to figure out if our model will make a mistake on that input. Okay, so essentially what we will do is we will look at the latent space and we will look at all the inputs of interest to us, and some of them will be classified correctly, some of them will be classified incorrectly. And what we will do is we will use this as our train set. So we will learn actually a linear classifier, and then kind of by essentially looking at the line perpendicular to this hyperplane, this will be our director of hardness. So essentially what we want to do is we want to solve this classification question, in which kind of we can predict by looking at the embedding of an image in the latent space whether the image will get classified correctly or incorrectly, and that's how we will infer our direction of hardness. So as a result, we now will have, okay, the hard exemplars are kind of, on this line, further on this line, so away from the hyperplane, and this will be exactly this, cats outside on the grass, and the easy exemplars will be the cats, inside. Okay, so that's point of start. But of course, when I say latent space, you immediately should think, okay, so what is the best latent space to choose? And of course, if you just use a standard deep neural network model, it has latent space that you can use, and everything works. But of course, you can do better. And I guess, now, in spirit of, of what many of us, including the previous work, wants to work with, is that, like, we turn our attention here to shared vision language space, like CLIP. Okay, so essentially what is nice when you are actually using the vision language latent space is not only that it's a very good space from the point of view of visual similarity, but actually now, as a bonus, we can also automatically generate captions too. So essentially, like, if we look at this latent space and we look at the different direction, we not only can kind of attribute images to them, but we can actually also find a way to generate captions that describe what they correspond to. Okay, so this way, this, once we train this SVM, this linear classifier, the corresponding caption corresponding to hard direction will tell us that this is a photo of a white cat on the grass, which, clearly conveys the right idea. And, the easy direction is a photo of a cat inside. Okay, so that's the point of start, and here you can see a bunch of examples of applying this, this approach automatically to different data sets. So for cats, this is, you already know what the bias is, but for dogs, you get that this is, essentially the difficult part are like Mexican hairless dogs inside. So kind of we know all the biases make sense here. We can do things for ImageNet, where kind of for fish, it's it's in particular that actually there's not that many close-ups of a fish in ImageNet, so it's kind of does worse on this. And of course, there is a plenty of images of a fish when someone holds them, so that's where it does well. There is the usual wolf kind of versus versus dog, or actually here it is it is something else, some other similar canine animals here. So all of this we surface similarly. There are also somewhat disturbingly biases and kind of in terms of a celeb A data set about kind of older women versus younger women, older men versus younger men, and so on. And even we can apply these things to to things like chest X-ray, where we also get some interesting biases about essentially the position that a given chest X-ray is taken. Although here we don't provide captions because they are not very meaningful, because just clip does not have the right terminology in it. Okay, so this is kind of the way to detect and name the failure, this systematic failure directions of our model. But now, of course, the next question is, okay, so once we detect and identify these hard directions, can we use this framework to also mitigate these identified failures? Okay, and in particular, we want to just intervene on these hard subpopulations, and the key idea, and maybe natural idea, is already just to leverage the fact that we have this text-to-image kind of generative models to get more training inputs. Okay, so essentially, if I learned that the caption for the hard subpopulation for my model is that a photo of a white cat on the grass, well, what I can do is I can put this kind of caption into my stable diffusion and get more images of the corresponding images, and essentially fine-tune my model using that. So that's a natural idea. The question is, how well does this work? And essentially it works well. So as you would imagine, fine-tuning on these hard-directed images, you increase the accuracy on the hard subpopulation. And the interesting part is that it actually does not seem to affect much, the general population, which it's mostly focused on this particular hard subpopulation that we are targeting, which is actually kind of nice. Okay, and then once you realize that this works, you can realize, okay, actually you can do even better. Instead of trying to go from this SVM, the caption of the hard direction, to a stable diffusion model, what you can do instead, you can realize, okay, well, actually you are getting directions in this shared image text space. So instead of going through the caption route, you can just directly take this direction and use it to decode the right image via the diffusion model. So specifically what you do is, if you have your baseline, a photo of a cat direction that corresponds to your whole class you are interested in, and then there is this found hard direction that we found via our SVM procedure, you can essentially get a synthesized hard image direction by just starting with the direction of the photo of a cat and tilting it towards its hard directions. And if you do that, you will go from this kind of a photo of a cat images to this synthesized hard images that start to pick up on these features that we know are important for, essentially are emblematic of our hard population. And again, this is kind of the kind of things you could do. And the question is how does it work? And the answer is, it works actually well. And essentially, the more you bias it towards the hard direction, the more successful the intervention is. Okay, so that's that's very quickly the first tool I wanted to bring to your attention. Now I would like to talk about the second one, which is essentially the model comparison framework. Okay, so essentially it's a framework for using a data-driven approach to really understand differences between different models. And I will explain in a moment what it is, and later on I will briefly connect it to distribution shift. So kind of the point of start here is this realization that our machine learning training pipeline has a lot of knobs. Okay, so when each time you deploy your model, you have to figure out what is the model architecture. Do you use transformers or ResNets? What is the training methodology, supervised, self-supervised, and then fine-tune? Again, that's a valid choice. You can think about the type of optimizer that you use, SGD or Adam, or what kind of exact learning rate schedule you use, or things like what kind of data argumentation schemes you use as well. Okay, again, we all have our standard choices for these, but these are choices, and the question is, which pipeline to choose. Okay, and of course, imagine I have kind of the framing for what I want to do is like, imagine there are just two pipelines to choose from. Maybe they just correspond to a binary choice of two ways of doing things, and how do we usually make the choice if we go with pipeline A or pipeline B? Well, either we don't really think about it and we just use whatever other library is using already, or maybe if you want to be a bit more principled, we kind of just look at what leads to better benchmark performance. And to be honest, that kind of did not work badly for us. We made quite a lot of progress in computer vision using this approach. But the question is, can you do better than that? Can we kind of go beyond this like relatively, kind of simplistic guidance of our choices? And essentially, this is what the goal of our work is. Essentially, the goal here is to provide a tool for pinpointing the pipeline difference via comparing the feature biases that the resulting models have. Okay, so essentially the point is that if I have pipeline A versus pipeline B choice, I can think about the models, that I will be training with pipeline A versus the model I will be training with pipeline B. And kind of what I want to do is I want to identify, input transformations, like two types of input transformations. One of them that essentially like input transformations that make the model A react to these transformations, but not model B. And then the other input transformation that does the vice versa, that essentially like it makes model B, affects the predictions of model B, but does not affect significantly, the predictions of model A. So kind of this is how we operationalize this goal of figuring out, in what way the feature, like what kind of feature biases model A versus model B have as a result of the different choices of the pipeline. Okay, so that's the goal. Now the question is, how do we go about finding such feature biases? And here we actually leverage a recent development from our group called Datamodels. Okay, so let me talk very briefly what data models are. Essentially, data models, they were motivated by the following scenario that, of course, I think many of us, would relate to, is in which we have some training set, we have some learning algorithm, and then we have some, input we would like to, have the resulting model make a prediction on. And kind of the question we might want to ask is saying, okay, not only like what the input of, my learning, of the model trained with my learning algorithm on the training set S is on this particular input, like what kind of output it produces, but actually we might want to understand how does training data and learning algorithm combine to yield this particular model output. Okay, and data model is essentially providing a framework for analyzing this kind of more fine-grained questions. Okay, so again, very briefly, what is a data model, or in particular, its linear variety? So kind of what, the object of interest here is this kind of model output function, fx of s prime, which essentially we think of, okay, f takes an argument, a specific input of interest x, and some subset of our training set S. And what it would like to tell us is, some interesting output, or like some output of interest of our model. So let's say, think of a margin of correct class. So kind of this function, it captures essentially how for a given, input of interest X, training on different subset of the training set, essentially like, how does it impact the given output of interest? Okay, so that's of course that's a very interesting function because it really allows us to understand, how training data feeds into this prediction. But of course, the problem is that, this function f can be very complex. It corresponds to really like training for each, to evaluate it. I need to train a model using my learning algorithm and look at the prediction. And the model is not simple, and also it's an extremely high-dimensional function because the space of the input is 2 to the size of the training set. So even for CFAR, it's 2 to the 50,000. For ImageNet, it's 2 to the over a million. So these are completely astronomical number. So this can be complex and hard to analyze. However, what we do is we show that in many cases it is possible to study a simple approximation of the function f. And this simple approximation of such a function f is called the data model. And in particular, quite often, what we can make this approximation be is actually we can approximate the behavior of this function via a linear function. So essentially, a function that kind of just that comes in a form in which it's just an indicator vector of the given subset of interest times some learned vector, which has just one weight per each training example in S. So essentially, like the output of a model on a given subset of the training set for a given input corresponds to essentially summing up the weights of the corresponding training examples in S that we are taking. Okay, so this was kind of a very fast, a very fast primer to data model. But the reason why I'm saying it is that it turns out the data models can be very useful for a variety of tasks. So especially when we can make them to be this kind of very simple, very simple linear models. So again, I will not go into it, but there is a number of ways in which we can use data models to get insight into inner working of the problem. But the one capability that will be useful here is that actually these data models, essentially these learned vectors theta x, they correspond to an embedding of the data points into Euclidean space, an embedding in which two inputs are similar if they end up being acted in a similar way by the same training example. So essentially, if kind of the impact of training examples on two inputs is similar, then we say this embedding tells us that these inputs themselves are similar, and we will actually use this, this embedding in what follows. Okay, so essentially, so how will we use this embedding? Well, essentially, we will say, okay, we have these two models A or two pipelines A and pipeline B. So for each input X of interest, and there will be many input of X of interest, we can look at kind of their data models embedding. Okay, so essentially these are just these big vectors that essentially for each have an entry for each training point, and this entry corresponds to the to this learned weight. That essentially think of this as influence of that training example on a given data point. Okay, and for different architecture, they are likely to be different. And now the key observation here is that even though the models now can be very different, in particular the latent space can be very different, this embedding lives in the same space because it's over the same training set. Okay, so even though the models can have very different characteristics, they might not even, maybe one of them is a deep learning model and the other one is some other kind of class of models, still this embedding is shared. So you really can make an apple to apples comparison in this space. And specifically, you take this like linear algebraic view in which, you view these two data model vectors as vectors. And then kind of you essentially find what we call the residual data model, which is essentially like we just, project one of these vectors, this embedding vectors, onto the null space, or essentially away from the other. So we kind of try to capture the residual output of model A that is not linearly explained by the output of the model B. Okay, so that's kind of this is kind of the simplest linear algebraic things you could do. And as a result, you are getting kind of like for each of the inputs, you are getting this kind of residual data models, and then you can run a PCA residual, PCA of these residual data models to extract this contrastive global trends in the data space. Okay, so essentially, as a result, you will get this kind of in space, you will get this residual direction that kind of are impact model A, but cannot to impact model B. And also symmetrically, you will get the residual directions that impact model B, but not model A. Okay, and now once you have this direction, once you have this direction identified in this, in this PCA space, you might ask, okay, so what kind of insights these directions allow us to get from data? And just to show you what you can do here is just like, let's focus on like one particular case study in which we essentially want to study the effect of pre-training on the performance of the model. So essentially our pipeline A or our model A corresponds to pre-training a model on an ImageNet data and then fine-tuning it on our target data of waterbirds dataset. And then our model B is just trying to, be like, essentially it's not using pre-training, it's just training from scratch on the waterbirds data. And now we kind of want to understand, okay, so when we make this choice of pre-training on ImageNet or not, well, we know it will impact performance, but what is happening, what potentially is happening from the point of view of, learned feature biases? Well, what we do is first we run this PCA on our residual data models and we get some directions. So again, these are the directions that impact the ImageNet pre-trained models, but not models trained from scratch. And here are the directions that impact models trained from scratch, but not ImageNet pre-trained models. And then we kind of, once we have these directions, well, we can project the embedding of all the images of interest on these directions and seeing which one tend to project more on the one space versus the other. So if we kind of project on the residual model, on the residual directions that kind of impact model A, but not impact model B, this is the kind of images we are starting to get. And as you will see, there is a clear pattern here that all these images tend to have backgrounds, faces in the background. So, this kind of should lead you to a hypothesis. Okay, so maybe this bias is that these models pre-trained on ImageNet are sensitive to the human faces. So you can essentially consider, like, just to test it, you can consider a feature transformation that literally pastes in the background a human face. And indeed, you will realize that, applying this transformation, this definitely impacts, the performance of the model A, but does not do much to the performance of the model B. So clearly, we already pinpointed one side of the feature bias difference. But then about, how can we find things that impact model B, so models that are not pre-trained, but do not impact the model that are pre-trained? Well, again, we apply the same methodology, just now in a symmetric way, and here are the images that end up impacting the not pre-trained models much more so than the pre-trained models. And as you see, one thing we notice here is that there is a lot of color yellow in these images. So to test that, we essentially consider a transformation that just simply adds a yellow square in the image. And we again see that it has this, quite significant impact on the not pre-trained models, but very negligible impact on the models that were pre-trained. Okay. So essentially, like we see, this is kind of one case study, but we see an emerging framework here in which we first kind of perform this analysis of the principal components of the residual data models. Then we kind of inspect data points that align with, with these residual PCS directions to identify features. And then we verify if indeed our conjecture is correct by, designing the corresponding feature transformation and doing counterfactual analysis. As you can see, the first part is fully algorithmic. The second and third step is a little bit, it requires some human involvement, so maybe that's not ideal, but it's still, at least we are able to help human intuitions here. And again, in the end, we can verify formally if a given conjecture indeed holds. And now, we can ask, okay, so now I have this framework, you can ask what other aspects can I use to compare it with. And in our paper, well, we do the pre-training that I already walk us through, but we also look at the impact of standard data augmentation, and we discover that essentially whenever you use things like random crops and flips, what happens is that you tend to kind of amplify, relying on texture of features. On texture features. So essentially, things to recognize spiders, you really are sensitive to the spider web texture, and kind of and this is kind of what happens if you don't use random crop. You are not as reliant on this kind of patterns. Okay, the other thing we do is the learning rate choice, like small versus large. And here we find that essentially a lower learning rate seems to amplify opportunistic learning, essentially like looking for shortcuts in the, in your learning, which kind of is in line with all of the previous work. And now, what does it have to do with distribution shift? Well, kind of the idea here is to say, okay, if I'm thinking that there is a distribution shift, the obvious intervention is to take my model that I trained in a standard way and then fine-tune it on the shifted data. Like that should kind of definitely align the model more in data set. So now essentially, if I think about applying this framework to comparing it to like the original model trained with my pipeline, and then the second thing is the original model after fine-tuning it on the shifted data, I can start getting insights about what is different, like what kind of features make my model different. So again, the previous framework did it in a bit more direct way, but here we're actually able to get, we have not done it yet, we should be able to essentially kind of pinpoint the differences or kind of the feature biases that the model that will be more robust to distribution shift will actually acquire. Okay, so essentially that's all I have to say. So just a few takeaways. I guess it will surprise no one that we really need to develop a robust toolkit for dealing with distribution shifts. It is something that we all talk about. I don't think there is a very reliable toolkit in place to deal with that, but hopefully we are all working on this. Today, I presented to you a framework that provides one approach for identifying and naming and intervening on such hard subpopulations via solving this, error prediction problem in the latent space of a model. And also, I told you about this model comparison primitive that might be a useful tool for getting a deeper, that is rooted in data and in features, insight into distribution shift. So, so that's all great. And, there was a previous talk that also provided some tools here. So this is extremely useful. But just one thing I want to call out, or kind of as a call of action, is that also as much as we should work on the toolkit, we should also, I think, work more on trying to conceptualize better what distribution shift is, because currently distribution shift is kind of this catch-all statement that everything is distribution shift, and the question is can we have a bit more fine-grained and nuanced understanding of the landscape here, so we can actually attune our thinking and tools to different strands, because it's very clear that not all of them are made the same, and you should finally start to really systematically recognize. Okay, that's all what I have to say. Thank you.
Thank you, Aleksander, for this great talk. Exciting results. For the audience, I'm looking into the Q&A part of the ECCV platform. In case you have any questions, please post them there. I'll first take the opportunity here to ask my own questions. Let me first ask one or two questions that are more of conceptual nature. The influence in your linear data model, the influence of one data sample, it kind of depends on all of the other samples, right? Is this so?
Yes,
but this is not handled. I mean, it's not like a sequential model, right? It's like you treat all of the samples as one set, right?
Yes. So this was the surprising part, is that so again, our framework explicitly wants to take into account this fact that exactly imagine I have two copies of the same image in my training set. Then if I just look at the impact of removing one of them from data set, it will be minimal. Even if actually this, two images, if I remove these two images, it could have a dramatic impact. The point is that what our framework does is it explicitly amounts for this. And it actually turns out that you can still get a pretty good linear approximation. So for instance, in this example I just mentioned, what would happen is that it would essentially split the influence of these two examples, half-half, among these examples. So you are right that you definitely should be very, very aware of this kind of, that you can't just, just focus on the leave one out influences. But it turns out that and this is what our framework does, that you can actually take into account these things. And that's really the surprising part, that there is this linear approximation that seems to do pretty good job of capturing this very non-easy and not obvious interactions here.
That's really interesting. Yeah, I still need to kind of wrap my head around this. I think surprisingly, it's kind of surprising.
I agree. We were surprised as well.
So, okay, maybe one more question regarding the first part. Or two questions. It kind of, if I understand it correctly, it kind of, so this SVM approach kind of relies on a property of models to tell when they are uncertain. Is this correct?
No, actually, this is something that we explicitly want to not do. It's just, again, all we want the model to tell us is essentially, or not even the model, but well, I guess the model, all we need is the information for the given inputs as we kind of deploy the model, is which things the model got right or wrong. Then we just look at this latent space, and then we solve this we just treat it as a supervised learning question. I'm just saying, here is a bunch of points. The ones that the model got right are positive. The one that the model got wrong is negative. And I'm just solving SVM, essentially linear classification question. Okay. So again, after that, from this problem that I solve, I could also try to get some notion of confidence, although this gets a little bit tricky, but we completely don't need that. We just look at this binary information, did the model get this right or did it get it wrong?
So then it's, okay. So in a sense, the SVM constraint, so basically in a sense, SVM on the feature embeddings kind of magically finds out which are the easy and the hard examples just based on the correct label.
Yes, and the reason is that again, this only works if this pattern of errors is consistent as viewed as the latent space. So if there are some very unusual errors, you will not catch this. This is only if there's a systematic distribution shift that is possible to visualize.
Okay. Here. Now this makes a lot of sense. And then final question from my side for now, wouldn't one solution just be using, I mean, later on you kind of rely on the clip model to describe the hard examples, but apparently the clip model can handle the hard examples, right? It can provide captions of, a cat on very difficult background. So shouldn't we just use the clip model in the first place? Well, to kind of classify the cat?
That's a great question. We did not, I don't think we run it as a baseline. That's actually a good question. I will need to think about that. Again, part of the reason here is just to even get an insight what's going wrong, but also the intervention here that you are getting is, okay, so you would say just fine-tune the model, essentially take clip and fine-tune the model on that. Is that what you are proposing?
Yeah, I mean, clip can tell me that it's a cat, right? Apparently. So, I mean, our classifier did not classify this cat on grass correctly, right? But clip can tell me that it's a cat on grass. So, apparently the clip embedding kind of has the ability to tell me it's a cat. So why not just?
Okay, I like this idea, and we will need to look into it.
It actually relates directly to what Carl presented earlier, and I'm just. Okay, so but you kind of didn't use clip as a baseline to kind of.
We didn't use it because we wanted to use it to kind of debug, other models, kind of create it in different models. But this is interesting to see But wait, okay, I will need to just double check.
Okay,
it might,
good.
As you can imagine, I was not the one running this experiment, so probably there, there might have been an experiment like this one.
Yeah.
But I don't
Let
know
me follow up with one more question here from Ophir, following the first question. I think the data model is similar to kernel methods. You have some feature function for pairs. Did you use this idea in your work? So how does this, I think it relates to, how does this relate to kernel methods, the data model idea?
Yes, so that's a good question. I don't know yet. Like it seems to suggest that there is some nice kernel that kind of captures the similarity measure that we are extracting, because again, we have this embedding and it's kind of nice. We have some ideas how to make it precise, but I wouldn't say I can really cast this connection in a precise way. But yes, it seems to hint that there is some underlying kernel that you can learn, and then just essentially like do your predictions based on that. But yeah, again, like I agree there is something there, but I cannot make it precise. How to draw the line exactly yet.
Good. Thanks, Ashwin. I think Ashwin de Silva raised.
Yeah. Hi, Professor Madry. Thank you for the great talk. I had a quick question about how to utilize data models in the context of detecting distribution shift. So you spoke about comparing different pipelines using data models having theta A, theta B, and then taking the residual data model and then ECA of that. So could we do the same for two different data sets, potentially having a distribution shift between them, and then explain the distribution shift between the two by looking at the residual data model?
Yeah, so this is a little bit tricky, right? Because if you just really, these data sets are trained on disjoint data sets, then, kind of this residual PCA direction, there will be trivial, because they just say, okay, if you are trained with this, like essentially like it may be harder to make sense of the geometry because there will be not much interesting insights there. So what the idea would be instead is at looking at image like models trained on the same initial training set, but then one of them gets fine-tuned on the shifted data set and the other does not. So this way they still kind of, we really are capturing like the space of the training set is the same, but you really are looking at the impact of getting fine-tuned on the shifted data set. And that's kind of, I think, what will provide you with a much more focused insight into, into what the difference is.
Right. So it assumes a latent space to begin with, then, from
sorry.
So it assumes a latent space from some other trained model that.
Well, data models, they don't assume latent space. Like that's what is actually nice about them. Is they just assume the same training space, because that's essentially what they really want to understand is, like essentially how different training points in your data set influence your prediction. And it turns out to be a good way to identify future biases. But it's very important to get interesting results is that this training space over which you generate this data models embedding is the same, is shared. So what should be different is the procedure in which you train the model, which again, in the first case would be just standard procedure of training. The other would be standard procedure of training plus fine-tuning on your shifted data.
Great, thank you.
Okay, so for the sake of time, we stop here. Aleksander, I think your secretary, Deborah, told me you might be able to join the panel discussion.
Yeah, I will.
Okay,
yes.
that would be in